the fundamental theorem of algebra, it says this. When you look at the polynomial, and it's a fundamental theorem, so it looks at any polynomial of any degree. So they look at it looks at the polynomial of degree n, and normally you write this in abstract terms like this. So your highest coefficient an, your next one a, n take 1. So basically you just link your index to the power of your z term. Of course, in general, you think of your coefficients as complex numbers, and you assume that the highest is non-zero. Otherwise, it's no longer the polynomial of degree n. So the polynomial of this, the degree of this polynomial is n. It's bigger than 1, bigger or equal than 1. So the fundamental theorem of algebra, it tells you that no matter what, no matter which equation you're looking at, there will always be a solution. Yes, so the first claim of this theorem says that there is always a solution. There's always a z-naught. Remember, this is a symbol which you read, there is, such that your polynomial will vanish on that particular number z. The theorem itself doesn't give you any ways how to find that solution. So from your point of view, like I said, from the practical point of view, it doesn't give you any, well, it doesn't represent any value. And like I said, there are even more discouraging results, which we discovered later after this theorem, which say that, in fact, it is in principle impossible to find the formula for the solution of any degree of any polynomial of degree higher than 4. It's called the Abel's theorem. It's a German mathematician. It's a very discouraging result, especially from your perspective. It says that as long, well, if you're looking at the polynomial of degree higher than 4, say 5, 6, or 7, you cannot find a general formula how to solve that. You can solve some of them, specific ones, by knowing some of the roots, by taking the quotients, by some other dirty tricks or good tricks. But just if you're looking for a formula, and you have to realize there was a stage in the mathematical history, and it's mostly linked with the Italian mathematicians. For instance, Cardano, it was a part of that stage when the people were really intensively hunting for this formulae for this. They found the formulae for the quadratics. They were very encouraged by that. Cardano found the formulae for the cubics by his beautiful trick. I'll show you that. I'll put the video up, and there's a handwritten solution. There was another Italian mathematician named Ferrari, like a car, yes, yeah, who discovered the formulae for the fourth equation. It was like the whole string of discoveries which encouraged people, well, discouraged them a lot, and they were hunting then for the fifth, and they couldn't. And then the gentleman named Abel came, and he just spoiled everything. Yes. So, in principle, I mean, it doesn't mean you cannot study the equations of higher degree. Just you have to realize that this elementary approach, when you hope for the formulae which will give you the answer, it's not the correct approach. The proper approach, in fact, was discovered by the other German, I think he's French, French mathematician, Évariste Galois. I don't know. Yes. That was the gentleman who was another it was another ingenious mathematician who discovered the proper way how to deal with the equations of higher degree, how to decide whether you can produce a formulae which give you the solutions, whether you can't produce a formulae which give you solutions, and how to find those solutions. But it's a totally different level of thinking. It's just, I mean, if you compare with your current level of thinking, when you need when you're hoping for the formula to solve the solution, it's like a totally next level of next generation of thinking. Some of you who will continue to study the algebra, higher algebra, probably will discover this or will master this level of thinking. Somebody will not. If you ask me, actually, I still have some gaps in my understanding of the way he was thinking. So it's not that easy, trust me. Right, so that's the general algebra, general things we have in relation to polynomials. From the practical point of view, what we have to realize for now, I mean, what kind of the implications for us from the fundamental theorem of algebra are the following ones. The theorem itself ensures that we have a solution. We cannot find that, but we have it. If in principle we do this quotient division, quotient method on the original polynomial with this known root, we can reduce the degree of that polynomial by 1, the way we did it with the previous example. So as a corollary of this general statement of the fundamental theorem of algebra, you can conclude that there is another polynomial, and I call it Q of z, such that P factors like this. This is something we just did with you on one particular example of a polynomial on the previous slide. And I showed you two methods how to do that, mine and the general one, if you like it or not. Now, you know that the degree of this new polynomial Q will be 1 less. Now, if you look back at the fundamental theorem of algebra, this new polynomial Q, it will also have a solution. And for this new polynomial, you can repeat this trick again. You can again divide this polynomial by the bracket carrying that new solution, and then you will reduce the degree of your quotient by 1 less again. And you will be able to keep doing that as long as you will have here a polynomial of some degree of 1 or larger. So this is sort of a mathematical induction sort of argument which tells you that you can in fact find not 1 but the whole n roots, and you can factor your polynomial in n by the method of mathematical induction. If you repeat these steps continuously, well, a few times, n times in fact, you will be able to conclude that you will have the whole n different, well, not necessarily different, the whole n roots, some of them may repeat itself, and your polynomial will factor into the product of linear brackets like this. This is the second conclusion we can draw from the fundamental theorem of algebra. From your point of view, there are a few questions in the yellow book where you need to factor the polynomial into product of linear factors.